Now that we've talked about the general calculation behind a transmitter-receiver pair in the form of the Friis transmission equation, let's take a look, let's extend that a little bit and look at the radar equation, which uses a lot of the same concepts and will help us understand a different set of applications for electromagnetics. So the radar application is using the same logic as the Friis transmission formula, except we're looking specifically in the situation where the source and the transmitter are in the same system, and what you're doing is you're sending out the signal and looking and detecting that same signal being reflected back at you to do something like observe UFOs or legitimate spacecraft. So this general concept applies to a large variety of systems, and the main characteristic is that the source and the transmitter are sitting in the same place, and you're using the measurement of the return in order to do some kind of sensing. Let's just follow through the same logic to derive the radar equation. So in the beginning, the radar will send out its transmitted wave, and so that's going to have the transmitted power times some kind of directivity, right? Directivity for the system. And then separately, once the signal gets out here, it's going to diffuse, right? And the power density is going to decrease. If this is a distance r away, it's going to decrease by a factor of what? Right, 4 pi r squared, right? The surface area of the sphere with radius r. And then now we're going to do something, we're going to define a new term, which is the radar cross-section. So the radar cross-section is basically what the signal looks like, how big the signal looks like to that particular electromagnetic wave. We often use the character sigma to describe that, conveniently, since that's also the character we often use for conductivity. But it will have a unit of meters squared. So this is basically it's a little bit like the effective area of an antenna, but basically the amount of energy, the amount of effective area that captures the power and reflects it back. And this is also a function, as you can imagine, this is also a function of the angle where the wave is coming from, right? So if my spacecraft was just a long, thin, conductive stick, you can imagine that if I'm coming in from this direction, I'm going to have a really large sigma as a lot of the waves get reflected. But if I'm coming from this direction, then it's not going to reflect quite as well, right? And so you have this radar cross-section. It adds a factor and then reflects it back. So you're going to get your reflected wave, which is now the transmitted times the directivity with the 4 pi r squared penalty, and then multiplied by this radar cross-section that tells you how much is reflected. And then the return signal, once it gets here, it's diffused by the penalty for the return trip, right? So you have your 4 pi r squared times sigma, right? As if you view this as a sphere and it's radiating out this way for the return signal, you take another 1 over 4 pi r squared hit to get back. And then finally, if you view this as the receive antenna, you now have your effective area, right? So ultimately, then the return signal is going to be the power transmitted times the directivity over 4 pi r squared, quantity squared, double penalty, times sigma, times the effective area. And that is our radar equation. So let's do some cleanup. So I'll rewrite it here. The received signal is going to be the transmitted signal, directivity, 1 over 4 pi r squared, sigma, 1 over 4 pi r squared, and then you have your effective area, which is lambda squared over 4 pi of d1, right? Because it's the same, presumably you're using the same antenna, and so these d's would be the same, and you end up with the radar equation, which is the received power is going to be the transmitted power, d squared, lambda squared, 4 pi to the third, and you have r to the fourth sigma. And this is the radar equation. So it's like the Friis transmission equation, except it tells you the amount of power that comes back for a given target for using the parameters that you have, the transmit power, the directivity. Now this directivity is both the transmit and the receive antenna. And then we also learned this new thing, this radar cross-section, which in an effective area-like way tells you how much of the power density is sent back the other way. And so if you're a UFO, and you don't want to be discovered by humans because of, like if you're a Star Trek UFO, because you have your prime directive that you need to follow and you don't want to interfere with the Earthlings, you want to make sure that you're very hard to detect, right? So, one way that you can do that is by just staying very far away. You see that distance is a much bigger penalty hit in the case of the radar equation compared to the link budget, because that same signal needs to take the round trip back, right? So your distance counts as double penalty because it also takes the penalty on the way back as well. But then separately, another thing that you can change as an alien is you can manage your radar cross-section, right? And so that's kind of one of the neat things is that the radar cross-section depends on a variety of factors: how much of the energy is absorbed, how much of the energy isn't reflected back the way it came. And so there's a lot of engineering you can do as an alien to tweak your radar cross-section. And one of the primary accomplishments is that if you look at the stealth fighters that are out there, many of them, even though you see that they're physically very, very large, they end up having the radar cross-section of a tiny bird. And so there's a lot of engineering opportunities here, but over here you also see the primary trade-offs and the link budget as it pertains to radar and other ranging systems.